The work is devoted to a numerical study of the behavior of vertically oriented eccentric electroelastic shells, containing a fluid in the gap between them. The solution of the problem is found in the framework of a three-dimensional formulation using the finite element method. The ideal compressible fluid is considered within the framework of a potential theory. The shells are made of the piezoelectric material polarized in the radial direction. The behavior of the thin-walled structures is described by the equations of linear electroelasticity. The distribution of the electric potential through the thickness is assumed linear. Here we proceed from the assumption that the shell surface is covered with thin weightless electrodes, which can either be shorted, which corresponds to the boundary condition, short-circuited, or disconnected, open-circuited. In the shell simulation, it is assumed that their curved surfaces can be represented with a reasonable degree of accuracy as a set of flat segments. The strains in each segment are determined according to the classical theory of thin plates. The study of the low natural frequencies and vibration modes is carried out for different variants of the kinematic and electric boundary conditions at the edges of the shells, the level of fluid in the gap and the eccentricity of the inner shell. It was demonstrated that both an increase in the misalignment of the shells and the fluid level in the annular gap and a decrease in the size of the gap itself are responsible for a decay of the lowest vibration frequencies. The electric boundary conditions corresponding to the open-circuited configuration lead to an increase in frequencies compared to the case of short-circuited configuration. The relative differences between the lowest frequencies for different variants of the electric boundary conditions as a function of eccentricity are of a qualitatively different character, which is associated with the boundary conditions at the edges of the shells, the size of the annular gap and the level of filling with the fluid.